Don't worry. Let's keep on going. So let's say we have a circle in the middle. Cool. That is metal. So you know the electric field line is perpendicular to the surface. Sorry, I missed another point. The electric field line and potential line never crosses. Sorry, this is not too as well organized as the section videos, because I actually prepared quite intensively for individual ones. I mean, I cannot read for 10 minutes and then go back to do that. I don't think I have enough time for that. Anyway, here is the metal. So we can, the one goes to here. I don't actually know if there's any better way of pointing it out. You can just following the line, like the perpendicular line, and then to figure it out. And we know that equipotential line is perpendicular to the. And also you know that the electric field line is going from positive to negative. So it looks like this. Maybe let's just not include this line to be more. That will be more confusing. So we know that the electric field line is perpendicular to the equipotential line. So perpendicular here, perpendicular here, perpendicular here. Perpendicular here, perpendicular here. Perpendicular, perpendicular, perpendicular. So, from this plot, can you tell which part have the strongest electric field? Here or here? Like for those two, one and up. Yeah, because it's denser. For the given space, there's more field line than here. Yeah. So that's the question. Yes. Any more concerns about electric field line? No. Cool. Right. Then we back to the lab. Which one again? Lab 4, lab 5.
Yes, maybe on 5. Yeah.
Yep, lab 5. Lab 5 is this magnet. This magnetic geo line, which is tricky when it's come to geological north and magnetic north. It's exactly the opposite. I just ruined the Earth. Okay, so here is geo north, geo south. I mean, it's almost the same point, but it's a little bit offset. That's a magnetic north. Magnetic south. I don't know. You can check back to any Google. Check on Google to see if I actually got it right. But I'm pretty, if I got it right, it's which angle it goes, but I'm pretty sure it's opposite. So you have almost like a bar magnetic field line. It's coming out of north, outside of Earth. It's coming out of the north back into the south. So which looks like this, right? Coming out of the north back in the south. What I mean by north and south, I'm talking about magnetic north and south. But inside is actually from south to north, as you can see. Yeah. So the deeping angle is just here. Actually it's roughly, I didn't draw a good picture. So the deeping angle is just the angle between the magnetic field line and the surface of the Earth. So if we have a magnet, something like that. I forgot the orientation. I have horrible sense of direction, so you can check back onto the video. I figure literally use 15 minutes to figure out which direction I'm going. So basically that's like, if we have magnetic probe, which is, let's just review the magnetic probe. Say if that's the case, we have south and north, the red always pointing towards the magnetic field line. So that'll be the arrow. And the angle between the magnetic field line and the surface of the Earth is the deeping angle. So that's the first knowledge point. The second knowledge point is slightly more challenging for me to draw. Right hand rule. So if you have a current going this way, you grab the bundle of the current, and you're using your right hand, and then your your finger is going at, or it's curling. The curling will be the magnetic field line, which looks like this. So I will try to draw a really unrealistic hand. Yeah, I just have a really big pinky. Yeah, something like that. So so here is our current, and there's our B field. So there's another typical example that that is used really often is solenoid. There's another way of using hand rule, but you don't need to remember that, or you can use another way that which I'm going to talk about later. You wrap around the current using your forefinger, and your thumb will be pointing at the B field. So you can also think that as for each wire, you analyze it using this right hand rule. So thumb is the current, and forefinger is curling at the magnetic field line, so which is like this. Oh, right? So you add everything up, it actually goes up. Every small wire, the magnetic field induced by every small wire, it will add up to the upward direction. So that's another common example of using right hand rule. And then, so far any question about this? No? Then let's go to the Lorentz force, which also utilize the right hand rule, but in a different way. Cool. So 3 Lorentz force QV cross B. So the way to see the orientation of the force, you can think, well, if there's a B going into the chalkboard, that means going into the chalkboard, and the velocity positively charged particle going to the right, you can wrap your finger first across the first vector V, and then across the second vector B. And then the sum is pointing at the direction of the B field. If you have a negative charged particle, of course, the force will flip because you have a negative sign. The vector's orientation flip. I don't know if there's any better way to illustrate it by drawing, but better than just drawing a hand. Really poorly constructed hand like this. Force. So wrap around first the voltage, and then cross to the B field, and then that's a force. That's the product, the orientation of the force. That's another right hand rule. Yeah. Oh, and also if you consider a stream of particle, which you can consider it equivalent to a current, right? So if you sum all the Q minus velocity, it's basically literally the current. So there we have a current going through this way, and the B field going inside. You will also have a force pointing upward. So that's, I think that's proportional to I cross B, right? So I think it's Ampere's law, right? So it's basically the same formula. That I is the orientation of the current flowing. So I cross F. Okay. Time is limited. Any questions? Cool. So many talks. Let's go to lab 6. Lab 6 is generator. I think. Yeah, generator. Basically, the core concept of that is just Faraday's law. Faraday's law, V equals to negative delta phi delta T. Phi is the magnetic flux. You know that it's equals to N dot B dot S. So that's how many turns for the coil that is turning that to generate the to generate the voltage and the the B is the strength of magnetic field, and S is the area of the coil. So we ended up having a voltage is proportional to the N B as omega sine omega t. So it's a sinusoidal function. You see, because you have omega t, sine omega t, and if the faster the turn, the brighter the light bulb is, or the more the voltage it come out, the more coil, the stronger, the bigger the area, the more voltage, the bigger the magnetic field, the more voltage should come out of it. That's quite straightforward, regardless that the detail of mathematics, please check on Lab 6 concept, AC generators. Anyway, the second concept I think is more, it requires a little bit more understanding, because that's our daily life thing, that related to our daily life, which is VRMS, root mean square is V naught over square root 2. The detail of that related calculus, which I explained on in the video as well, the concept, average power. So we have for the AC power supply, the power is equal to V naught over 2R, V naught square over 2R, or VRMS square over R. By putting it into a graphical understanding, that what I mean by V naught and VRMS is, here is our AC power supply. That's what really is symmetric. I mean, you got the idea. It's sinusoidal function. The maximum is V naught. So if you want to, the total, if you want to power this with DC power supply, you can power it with the voltage of VRMS. So essentially, if you put a light bulb into a AC voltage of V naught, it will shine as bright as a DC voltage with a voltage of V naught over square root 2. That's like what it means for the RMS. For this scenario, it's basically, if you want the same power but DC, you just need that voltage to achieve the same power output. Yeah, that is the core concept that I'm concerned about on Lab 6. Then let's go to Lab 7, which is more interesting, or also you're more familiar with. Maybe I can speed up a little bit, because time is almost running out. So far, any questions? Cool. Of course, you can ask me into the office hour or next week. Lab 6 is refraction. Sorry, Lab 7 is refraction and total internal reflection. How is my camera doing? still running. Surprise. So as all of the concept is rotating around a Snell's law. N1 sine theta 1 equals to N2 sine theta 2. So what it happens is, is if we have N1, N2, and there's a condition of N1 greater than N2, you know that is sine theta is